want to continue with our discussion of matrix algebra to define what is a determinant, to understand determinants, because to derive Cassini's identity in the course, we use the concept of determinants. So let's see what a determinant is. The easiest way to explain what a determinant is to look at a system of first-order equations. Ax plus by equals 0, cx plus dy equals 0. X and y are the variables. A, B, C, D are the known coefficients. And here the right-hand side is identically 0. We can take this system of equations and write it as a matrix equation. So remember our matrix multiplication. This is A, B, C, D times the column vector xy equals 0 as a column vector. So when the question that brings in the determinant is, when does there exist a non-trivial solution for x and y in these equations? The trivial solution is just x equals 0, y equals 0, because then we know we get 0 equals 0. So when does there exist a non-trivial solution? Well, we can manipulate these two equations. We can eliminate y if we multiply the second equation by b and the first equation by d, and then subtract the second equation from the first equation. We get rid of y. That will give us AD minus BCX equals 0. Or we can get rid of x. We can multiply the first equation by c and the second equation by a, subtract the first equation from the second equation, and we get AD minus BC times y equals 0. So in order for the solution of these two equations to be different than x equals y equals 0, we would require that AD minus BC equals 0. So there exists a non-trivial solution when AD minus BC equals 0. That's exactly how we define the determinant of a matrix. So we define the determinant of the matrix A, B, C, D by AD minus BC. How do we view this? We multiply the diagonal elements AD, and then we subtract the multiplication of the off-diagonal elements BC. So that's all there is for the 2 by 2 case. If you wanted to do higher dimension, you can extend the definition to higher dimension, as long as the matrix is square, n by n, say, but we don't need that for this class. So we'll just stay with the 2 by 2 case. So the theorem we need to prove Cassini's identity is that the determinant of the product of two matrices is equal to the product of the determinants. So the determinant of the matrix A times B is equal to the determinant of A times the determinant of B. We need this only for 2 by 2 matrices. So even though this is a general result for A and B n by n matrices, we need to only prove it for the purpose of this class for 2 by 2 matrices. So I think the easiest way to prove this statement is just to do the calculation. So let's see how it works. We introduce two matrices. Matrix A has elements A, B, C, D. And matrix B has elements E, F, G, H, right? We can take the product of the matrices. So we multiply A times B. So we'll go across the rows of A and across the columns of B. So we have, here we have AE times plus BG, AF plus BH here, CE plus DG here, CF plus DH here. Okay, so we get the product matrix. Then we're looking at the determinant of AB. So the determinant of AB is the product of the diagonal elements minus the product of the off-diagonal elements. We get this expansion. We can do all of the multiplication. So let's do all of the multiplication. And we get this expression. If you want to do the algebra correctly, you have to think how to order the terms. So alphabetical order, I think, is a good idea. A, B, C, D, E, F, G, H. Always keep it in alphabetical order. We can do the expansion. We get 4 terms from each of these products. We have a minus sign here, so we can look for a cancellation. And in fact, ACEF exactly cancels ACEF. And the other 2 don't cancel, but the 4th one, BDGH, cancels BDGH. So we can do the cancellation. So we're left with 4 terms. 4 terms here. We're trying to find determinant of A times determinant of B, so we can do some nice factoring here. We can factor these terms. So we can factor out an AD, so AD, then we get EH minus FG, and we can factor out a BC, so then we get, if we put a minus sign here, then we get from this BC EH minus this FG. And both of these terms then contain an EH minus FG. So we can factor that one out. And we get AD minus BC times EH minus FG. So we're getting what we want. So this AD minus BC is the determinant of A, and EH minus FG is the determinant of B. So we get the determinant of A times the determinant of B. So we've proved then that the determinant of AB, the product AB, is equal to the determinant of A times the determinant of B for the 2-by-2 case. And this is exactly what we need to prove Cassini's identity.